Good morning, students. So in the previous class, we were discussing about the ARM architecture. So with a block diagram. So next we need to discuss about the, when you are going to write the program, we need to discuss about the instruction formats. I mean what are the different instruction we have. Because we need to discuss with the instructions and different architecture. We started with the ARM architecture. So in the ARM architecture, what are the different type of the instructions? Okay, so in the previous class, till the previous class, we were discussing, we focused on the hardware fundamentals of the actual ARM processor. The ARM processor can be here abstracted into 8 components as in the block diagram what sir showed in the previous. We have a ALU, we have barrel shifter, we have MAC, register file, instruction decoder, address register, incrementer and the sign extend. And also we discussed about the 7 processor modes and also the two instruction sets, thumb instruction which is of 16-bit instruction length and ARM instruction which is of 32 instruction, and also we have a Jazz instruction set which is have 8-bit instructions where we are using to execute the Java bytecodes. But we discussed about thumb and ARM architecture, ARM instructions. And also in the previous class we discussed about the register bank, register file, and we discussed about all the 37 register. Out of the 37 registers, around 7 to 18 are the available register and other registers are the banked register. So those registers are used when you are executing, when you are using different processor modes. Different processor modes. And the current processor mode, the CPSR, is stored in the CPSR register. CPSR is current processor stored register, and CPSR holds the current state of the processor. The current state means the program is in which mode, either it is a user mode or it is a system mode or it is a IRQ mode, FIQ mode, different interrupts mode, etc. And also the processor core as well interrupt mask condition flags and the states. So we discussed all the 32 bits of the CPSR register in the previous. So when we are executing any one instructions, we need to see the contents of the CPSR register. So that will be discussed in the class. And here the state determines which instruction is being executing. So now, in today's class, we need before starting the actual instruction set. So we have a lot of instructions like arithmetic instruction and different multiply instruction, branch instructions, etc. Okay, before discussing actual instruction set, first we'll have a look how we can have a program structure, how to write the program in the ARM processor. The same program structure we are following in the MPCA lab also. Okay, one, and sir has explained by taking one simple example how the program structure is there, what are the contents of the CPSR register for each instruction and what are the contents of the memory location and what are the different instructions. Okay, so in this case we are using few instruction which is uh, using for only that particular program. So from next class we'll discuss all the instruction set of the ARM processor. So we'll have a look with the source video. I hope I am audible. Yes?
Yes, ma'am.
Yes?
You're audible, ma'am.
Okay.
Hello everyone, greetings for the day. Welcome to the fifth session of Microprocessor and Compute Architecture course. In this session, we'll understand the ARM program structure and the instruction format. It means to say that now we'll start programming the ARM processor. Till now, what we have studied is the block diagram of the ARM processor, the different modes in which the processor can be executed, the register bank, different type of registers, CPSR, SPSR, thumb mode, thumb state of execution, all those things we have seen in the previous sessions. In this session, we'll dedicate our time to understand the ARM program structure and the ARM instruction format. So here is the structure of the ARM program. The ARM program is divided into two parts, the text part and the data part. The text part will have the instructions which forms the program, and the data part which is used to declare the data or the variable which is used in the program. Even the assignment can be done at the data part. Whatever you are seeing in the blue color are the instructions which a user need to write to form the program. Towards the left hand side, whatever you are seeing in the red color is nothing but the address which is assigned to each instruction in the memory, so that this instruction can be fetched and it can be given for execution. Not only for the instruction, the address is assigned to each data which is declared and assigned a value in the program. For example, we can see here, I have a small program which will add two numbers A and B and store in.
And students, here when you are writing the program, excuse me, when you are writing the program, you will write only the instructions which are in blue color. Okay, only these instructions you are writing. Okay, you are not writing, want to write the red part.
The variable called C. So you can see in the data part, I have declared a variable A of size word, that is 32-bit, and the value is assigned as 100. And I have a variable B, again which is of word size, that is 32-bit, 200 value is stored in B. And I have a program variable C, again which is of word size, and it is initialized to 0. The address of the variable A is 1028. The address of the variable B is 1029. Address of C is 1028. How this address is computed, how to understand this address, I'll explain you in the later part. But as of now, you understand 1028 is the address of A, 1029 is the address of B, and 102A is the address of C. That is the data part. Coming to the instruction part, the first instruction, LDR, is nothing but the load instruction. So what is happening here? The register R0 is copied with the address of the A. That means that 1028 is loaded to R0. Similarly,
See, in this case, so this is the instruction part. This part is the instruction part, and This is the data path. I mean, we are assigning the values here. So this address is actually the user or the programmer are not going to write this address when you are loading the program into the computer. Once it is converted to the machine language, the proper address is assigned, and this is actually the instruction. So that this part we need to see later, how we are encoding the instruction. This is the encoded instruction of the LDR on these instructions. And suppose if I take the first instruction, load the address of A to the R0. R0, R1, R3, R4 are the registers. When you are executing the program here, so we are using, as we discussed, we are using 37 register. Out of 37 register, only 17 or 18 registers are accessible at any point of time. Others are the banked registers. So we use register R0 to R13 and R12, and R13, 14, 15 are used for stack pointer, linked register, and the program counter PC. So now in this case we are using the registers R0, R1 and R3, R4, R5, R6, and PC points to the address of the next instruction. Initially PC points to the address of the first instruction. So what is the address of the first instruction? Address of the first instruction is, in this case it is 1000. In our program it is 1000, but it may change. The program will be loaded wherever the memory is free. We don't know. Suppose if it is a multi-programming concept, where if the memory, so assume this is the memory, if it is a memory, so our program is executing in this case. So at this time, and we don't know the address of this particular location. So from here our program is going to start. So here that will be discussed here, and you can see the value of the PC also in the next slide. So initially R0 holds the address of the A, not the content of the A. See the address, the red color shows the address of the A. So 1028, okay, 1028 is the address of A. I mean R0 will be having 1028, R1 will be having 1029, and equal to C is nothing but address of C. Address of C holds the value of R3, holds the address of the C. So later here LDR R4 and within the bracket R1, that means load the value content of R1. The square bracket shows equal specified, denotes the address. The square bracket denotes the content. The content of R1. See the content of R1 here, actually that is R1 is having 1029. In 1029 content of R1 is 200. So it stores like this. And sir is also explained the same. Just we'll see the video, then the other things I'll explain.
In the instruction 2, the
Ma'am, the video is frozen.
the address of R1 will be copied to R4. So R4 now will have the value which is in the address referred by R1. R1 contain the address. So R1 has the address of B. That means that R4 will have the value 200. Similarly, R5 will have the value 100. The add instruction will add R4 and R5 and copy it to R6. So R6 will have the value 300. The last instruction tells that it's a store instruction. It will store the result which is in R6 to the address which is having in the register R3. That means that the result 300 will be copied to the memory location called C. So this is the general structure of the program. You can relate the first slide and the second slide to understand how the program need to be written. Coming to the data type, as I told you in the beginning itself, the ARM data can be of byte or it can be of word, that is 16-bit, or it can be a word. If you want to store the string, it will be of 1 bit, and the uh, terminology what I use here is the ASCII Z, which is used to represent the string that we'll understand in the later part. So this is how the instructions will look like. So I have a screenshot of the ARM simulator which is used in your lab just to show the how the address are copied into the register. You can see in the screenshot R0 has the value 1028, that is nothing but the address of the variable A, which is the output of the first instruction LDR R0 equal to A. So A address is copied to R0. So R0 is 1028, which is nothing but the address of variable A. Similarly, R1 has the address 1029, which is nothing but the address of B. R3 contain 102A, which is nothing but the address of C. So ultimately, if you see R4, R5 and R6, you have hexadecimal 100, 200 and 300, which is stored in R4, R5 and R6 respectively. Right. So this is the general structure of the program. This is how you need to understand the instruction or the program which is written for the R.
As students, I hope the structure is clear. Sir has explained by taking one simple example, and in the program we'll be having two parts here. One is dot text. Dot text is used to write the instructions, and dot data is assign the values. So here we have a variables a, b and c, and we need to give the values of a value is 100, b value is 200, and c we need to calculate. Initially it is 0, we have initialized with 0, and all other what is LDR, add, STR, or just we discussed only for this particular instruction. Next class we're discussing the over all the instruction set in the ARM processor. So any doubts with this small program? Equal is the address and the square bracket denotes the contents of the register. Yes, I hope it is clear. And the red color shows the address, and after the colon here it shows the encoded instruction. So for example, EF9F0014 as in the first instruction, that is equivalent to LDR R0 comma equal to A. That we'll discuss after completing the instruction, the how to encode the instructions. Okay, and here the starting address in this program what we are giving is 1000, then it is incremented by 10048C, because ARM processor is a 32-bit instruction. Okay, ARM is a 32-bit instruction. Each instruction is of 32 bits, I mean 4 bytes, and anyway it is byte addressability. 1000 plus 4 byte 1048C, it continues. Okay, but when you're taking the data in the memory 1028, I mean the computer memory, the address 1028, it is having the value 100, 1029 having a value 200. Okay, so here it is not increasing because it is not instruction. A word 100 is not a instruction, that is the value we are giving. Okay, sorry.
ARM processor. So some features of our instructions. Already you understood that each instruction is of 32-bit wide, and this is the load and store architecture. We have dedicated instruction for loading and storing, bringing the data from the memory and storing the data back into the memory. And each instruction will have 3 address, one for the destination and the 2 operand. The fourth statement is important for me. What it says, conditional execution of every instruction. Every instruction is executed in the conditional execution state. What do you mean by conditional execution? Please underline it. We are going to understand this in the next coming slides. Also, when I'm doing the load and store, what I showed you in the previous example is loading and storing a single data. But in our programming, you can load and store multiple data into the register and from register back to the memory. So this is one of the extra feature what we have in the ARM processor. Then when you saw the block diagram, you saw that the ALU will take 2 input, out of which 1 input will be through the barrel shifter. So we don't have a shift operation separately here, but any ALU input will go through the barrel shifter. If I want to shift anything, I can embed that shifting operation in the any existing instruction. Last one is that there is no memory to memory operation. Whatever data you want to work on, whatever instruction you want to work on, the data should be in the register, not in the memory. Memory to memory operation is not done in the using the ARM instructions. Coming to the general format of the instruction, the general format will start with the mnemonics, followed by optional condition, followed by optional S, a suffix S, and RD is the register used for a destination storing the result, operand 1 and operand 2. Operand 1, either it should be a register or the immediate value. Again, when it comes to operand 2, again it can be immediate value or a register with the shift, optional shift operation. This is common, this is understood. RD, operand 1 and operand 2 are understood. You can relate that with the MIPS instruction which you studied in the previous semester. Only difference is that the second operand can be accommodated with the shift operation, which we are going to see in the later part. So coming to the mnemonics. Mnemonics tells is nothing but the operation which you want to execute. It can be add, sum, mul, anything, comparison, logical operations, anything. Everything will have the dedicated opcode which you need to use it. Then comes the condition. Condition is optional. As I told you, every instruction in the ARM will execute in the condition state. It is a optional thing. It is used for the control, right? So the conditions can be EQ, that is equal, MI for negative, GT for greater than, LT is less than, LE is less than or equal to, NE is not equal to, AL is for always. That means that if I write AL, or if you don't write anything in the condition field, the instruction will execute all the time. If I write
Students here, as in the second part condition, the mnemonic field is a instruction, actual instruction, add instruction, sub instruction, mul, add s, add I, etc. All the instructions are the first part of the instruction format. So the general instruction format which is showed in the blue color that is the instruction format. First we will write add sub. Condition means suppose add EQ or add MI, add GT, sub LT. Okay, subtract if it is less than. If it is less than means before that instruction will have a comparison instruction. Then followed by S. For example, add S. Okay, I can write add and condition is optional. Suppose if I am not using any condition, add followed by S. So S will see what is the S actually here. Then RD is a destination register. Okay, then operand 1, operand 2. For example, add R3, R1, R2. R3 is a register, operand 1 is a R2. Operand 2 is a R1. Operand 1 and 2 are the registers or it is a memory location or it is a immediate value also. So now coming to the point S here. Okay. S is an optional suffix. So if S is specified, condition flags are updated in the result of the operand in the CPSR register. So we have seen the format of the CPSR in the previous class, 32-bit instruction CPSR. In that the starting four values are 27, 28, 29, 30, 31 bit are NZCVQ, negative, 0, or it is a carry, overflow, then it is a saturation. Okay. So those bits are updated if we have a instruction, if we are writing the instruction. So for example here, suppose if I write here add okay, sorry for the interruption. Suppose if I write add s, okay, so then add s, let me take this. So either I can write add. This is one normal instruction. So I can write add s. So what is the difference here? Okay, add is normal add instruction, and suppose if you are adding, for example, add -4 then -5, the result is -9. So whatever it is, the result is negative here. But we are adding. This is general for your exam, for your understanding purpose. Then the result field is n should be 1 negative. So now if we are not adding s, no, the flags are not updated in the CPSR register. If it is add s, the flags are updated in the CPSR register, that you can see while executing the instruction. Okay. For the same example also we will see in the source video. And when we are looking with the conditions, so what is a conditional execution here? Conditional execution controls whether or not the core will execute an instruction. Based on the condition flags, our actual instruction is going to execute. Most instructions have a condition attribute that determines if the core will execute if it is based on the setting of the condition flags. So what are the condition flags here? We have NZCV, negative, 0, carry, overflow. So prior to the execution, the processor compares the condition attribute with the condition flags in the CPSR register. If they match, then the instruction is executed. Otherwise, the instruction is ignored here. So for this also we will have a example how it is executing based on the condition.
EQ, that means that if the previous instruction, if it is a comparative instruction, if it generate the result as equal, then only the next instruction will be executed. If the previous instruction generate the output as negative, then only the next instruction will be executed. Those type of conditions.
See, EQ means suppose I'll take add EQ. We are not going to write only EQ. I mean mnemonic is add followed by condition is EQ. Add EQ. There is no space. Okay. Add EQ S. S is also optional here. Add EQS. That means we are adding if the operands are equal. How to check whether they are equal or not? We will be having that in the previous just previous instruction. S means the flags will be updated in the CPSR register.
Should be satisfied to execute the next instruction. So this status I'll get from the CPSR register. That's what we studied the CPSR register in the previous session. So we have N, V, O, C values, right? So based on that, we set we decide whether it is equal, less than or equal to, less than or not equal to, something like that. Then comes the S bit. S is a suffix which is used in any instruction, which will decide if I write S in my instruction, it will modify the CPSR register or the status register. If S is not mentioned, then the CPSR register will not be updated. If you want to execute your program in the conditional mode, then you need to specify S in your instruction. If you specify S in your instruction, the CPSR will be set if the result is 0, if the result is negative, if the result is overflowing, or if it generates the carry, right? So we'll see that one by one. Now, again coming to the screenshot of your ARM sim, which shows the register content and the CPSR register value. You can see here the CPSR register value, which has N, Z, C, and V, which is initialized to 0. You need to remember that CPSR format. So if the output of this program, if it is negative or 0 or carry or overflow, one of the bit will get set. This is not by default. If the add instruction has the, if I would have used the suffix S there in the add instruction, then this CPSR register would have get updated. In this case, I have -10 in R0 and -10 in R1. When I'm adding R1 and R2, I get -20. R2 has -20, you can see there. R1 has -10, R0 has -10. Though it is generating the negative result, the N bit is not set here. Why? Because the suffix S is not included in the add instruction. Coming to this example, has -10, R0 has -10.
See, for this instruction, so in the example we have 3 instruction. Okay, for add R2, we need to initialize the value of R1 and R0 because R2 is a destination instruction. So add R2, R1, R0. So this is the instruction format. In the instruction format, we have a mnemonic instruction and we don't have any conditions here, and we don't have S suffix S also. Okay, as in the previous we have an instruction format. Then we have 3. One is a destination register and 2 are the source operand, and both are registers here. Okay, so now for add, and the right side is a content of the CPSR register. Okay, and as we know, R0 to R15 are generally we are using the registers for our operations, and you can see in the down the CPSR register, and we have the CPSR negative, 0, carry, overflow, all or 0, because nothing is set, because in the instruction the suffix s is not there. If suffix s is there, means CPSR register would have updated here. And IRQ is disabled, thumb instruction 0, CPU mode is system mode here. This is the contents of the CPSR register. And I mean flags and the which system mode of the instruction. And coming to the registers, out of R0 to R15 we are using only 3 register: R0, R1, R2 and the PC. PC is used with all the instruction. Here the current value of the PC is 70656, because from there the program is going to start, and just ignore about the stack pointer there. Okay, so initially R0 is minus 10, R1 is also minus 10. After adding, R2 sets the value 20. Even though the value is negative, it is not showing because add s is not there. So that difference is there in the next slide.
Yes. 10. Though it is generating the negative result, the n bit is not set here. Why? Because the suffix s is not included in the add instruction. Coming to this example, I have add operation, same add operation, but I have a s suffix in my instruction. S tells that I need to update the CPSR register. Same program, when I execute, the output generated is minus 20, which is negative. So you can see in the CPSR register, n bit is set to 1. Coming to the next example, here I have the add instruction with the condition and the suffix s. Mi is the condition which tells that if the previous result is negative, then only execute the instruction add. So sub s is nothing but it will subtract R0 and R1. If the result generated is negative, then the add instruction will get executed. So you can see here the sub instruction generate the output as minus 48. R0 is 40, R1 is 4, minus 40, minus 40, minus 4, and when you add it, R0 and R1, you get the negative value, right? So if n is set to 1 here, since n is set to 1, that is the result is negative, then only add instruction is executed. That's what you are getting the value 48. In this case, you can see since n is set to 1, that is the result is negative, and when you add it,
okay, see one more instruction here. So in this case, dot text is we are having only the instruction, and dot end is it's a programming structure. So initially move R0 comma hash immediate value. Hash means immediate value. So now R0 is actually minus 44, okay, in the program, but in the right side that is the final value. The value starts showing the final value. Initially R0 is minus 44, then R1 is actually plus 4, it is plus 4. So next the third instruction is sub s. Sub is a subtract. S means the contents are modified in the CPSR register. You can see right side CPSR register. the values are modified. I mean, it is showing -1. N becomes 1. If only sub is there, it will show only the 0. It is not updated. The values are, even though the value will be 1, but it is not updated in the CPSR register. So with sub S, so what happened here? R2 is R0 minus R1. I mean minus 44 minus 4. The result is minus 48. So in the right side you can see R2 is a minus 48. So now the value of the result is minus. So see the fourth instruction, add MIS. Add is a add instruction. MI is if the result is minus. Okay, mi is either negative or it is a minus. If the previous result is negative, then only this add instruction will execute. So I hope you are getting this. Okay, S means again the contents are values are updated in the CPSR register. So anyway, here from the sub instruction R2 is minus 48, the result is negative. Add instruction will execute. Add R0 comma R0 comma R1. So value will be, destination is R0. Value of R1 is minus 44. R0, R1 is 4, minus 44 plus 4 is minus 40. So that is showed in R0. The final value of R0 in the right side is minus 40. So that is the final value. So this is executing. See the instruction add MIS. Add if the result, previous result is negative, S is update. So next one we'll see if the result is not negative. So what will happen?
R0 and R1, you get the negative value, right? So if R2 is 48, R2 is 48, the result 44 minus of minus 4, that is you get 48. So the output of the sub instruction is not negative. So the
See here also same thing. Initially, what is the value of R0? R0 is plus 44. Okay. And R1 is minus 4. Then we are subtracting. Subtracting R0 minus R4. So what will happen here? For R0 minus R1, R0 is 44, minus of minus 4 will get 48. So R2 is a positive value here. And next we have the result is positive, but see the fourth instruction add MIS. This particular instruction is going to execute if the result is, the previous result is negative, but previous result is 48 which is plus, then it is not going to execute the instruction. So R0 will be having 44 itself. Otherwise R0, the R0 will be having R0 plus R1. So we'll get 44 minus 4 which can be 40 itself. Now it is not executing. Final value of R0 is 44 itself.
n bit is not set. Since n bit is not set, add operation is not happening, or add operation will not be executed here. So you need to understand the instructions like that. So this is called the conditional execution, right? The condition and the S is optional. So if you want to write, if you want to use the condition option, you can mention the condition. We'll get into the details when you understand the instruction format and the encoding technique. You'll understand better, but you need to understand how the instruction work here. So the last example, which is I don't have the S suffix here for any of the program, but I have a comparison operation, compare R0 and R1. If it is not same, then it will set the negative value here. If the value is, if the comparison of R1 and R2 is not same, the negative n bit will be set of your CPSR register, though you are not mentioning the S here. So when I compare R0 and R1, which is 4 and 44, 4 minus 44, you get a minus 40. So the n bit will be set. So the comparison will set the n bit here. So if the n bit is set, then that means to say that these two numbers are not equal. Add operation will happen, R0 and R1 will happen only the previous comparison instruction is same. If it is equal, add EQ means add if the previous instruction results in equal. Since it is not equal, you can see here add operation is not executed. R0 and R1 remain same, 44 and 4 here, right? So with that introduction to the program structure and the instruction, general format of the instruction. Next, we'll move on to understanding the instruction set in the ARM processor. In the ARM processor, instruction sets are divided into data processing instruction, data transfer instruction, block transfer instruction, branch instruction, multiply instruction, and the software interrupt instruction. So we'll look into this instruction one by one from the next class with the programming examples, right? So in the next session, we'll look at the first set of instructions, which are nothing but the data processing instruction. I've given few references. You can go through the references so that you will understand the class. If you go through the reference, if you read it and come in the next session, we can you can understand the things better, the instruction sets, right? So we'll start with the instruction set in the next session. Data processing instruction will.
Okay, students. In this class, we have seen how the structure of the program. But when you want to write the program for any task, we need to know what are the different instructions we have. If you know the instruction and which are the flags we are using and what are the different instruction formats, how the instructions work, then only you can write the program. So from the next class, we'll discuss all the 6 types of the instructions. Okay, that is the instruction, and we'll start with the data processing instructions. Okay, thank you.